Okay, before we begin with the content, let's talk about next week. Next week on this same time, we will have the midterm exam. All right, you will have 2 hours to do the exams, and we will still use class marker to do the online exam. What else? There will be 40 multiple response questions. This time, I think I'll make it this way. That is, the partially correct answers will be awarded with scores proportionally. But if you choose wrong answers, then you will not get those scores. So there are no deductions. It's better than last time that you have that you guys had the exam on data model, right? Because at that time, if you make like partial, if you did not answer all the correct answers, you will not get the score. But this time, let's say you got partial, okay? Right, and there will be 40 of them. You will get 2 hours to do that. And the same as last time, you can search. Actually, you must search the internet. Particularly, you need to look at the documentation in order to be able to answer some of the questions. So it's more of the open world question, open world exam that just like when you work in real environments. Right, so that's about it. Another thing is that for this video, I promise that I'll upload it within this afternoon, because you can have times to review them before the midterm exams next week. Let's talk about the midterm exam first. Do you have any questions about the midterm exam? The contents that will be in the midterm exam include everything until this point. No, I should say everything until the end of this lecture. Yeah, that's more like it. Any questions you want to talk about first? I asked you just to first not talk to your friends during the exam, work on the exam yourself. I have no ability to control that. Even though I know, even though I asked you guys to open, to turn on the cameras, let's say that there are plenty ways. If you want to cheat the exam, you can do that. But I'll trust you guys on that, and you got 2 hours to do that. Anyway, the mostly in my class, the grades does not really comes from directly that's not directly correlate with just the exam. You need to do the project well, and actually projects was almost equivalent to the exam. The same goes for the assignment, the labs. If you submit the labs on time, do every and then also perform every of them well, then that's another part that is actually equivalent to the exams. So that's about it. Anything you want to talk about first before we begin with the content today? Right. Otherwise, let us start with today's topics. Today's topics will be on MapReduce, and I would say a way that you can write a program on big data system. If we talk about big data Hadoop version 1, and I would say that it is a type of framework that when you take a look at big data, it is quite native in terms of the computing, the way that you perform computing, and also the way that you can create a processing of data. So when learning MapReduce, it will take you a step further toward learning big data framework, everything in the whole sense. You will see a lot of tools, a number of tools that will be used on the different tasks. Many of those relies on MapReduce as the basis, as the underlying algorithm that allows them to perform the task. For example, after the midterms, Ajahn Rashwit will be the main lecturer. He's actually a lot funnier than me in terms of teaching. So yeah, I think I hope that you get good times learning from him. Uh, and uh, and he'll introduce you to Hive, another tools, another big data tools that use MapReduce as the underlying algorithm to perform the task. And we will talk about that a little bit here as well. So that's what about today, right? Today I will introduce you to the basic algorithm, the basic concepts of MapReduce, and we will talk about the architecture related issues of MapReduce. What are job trackers? What are task trackers? And the version tools, application and resource manager. We will talk about them, right? So let's start. We have seen last time that Hadoop, particularly the Hadoop distributed file system, allow you to store file in the distributed manner so that you can perform access, you can perform read and write faster than having having the file storing in just one node, right? By spreading them through multiple nodes, you can also spread the computation through multiple nodes as well. So with the same concept, Hadoop will allow you to have the not just the storage but also the processing of the large data set by distribute the processing along with the data so that you can move the computation to the place that you store the data, and that will be more efficient if you think about it that way, right? So let me recap a bit about Hadoop. Last time we talked about this architecture that in order to use Hadoop and configure the Hadoop architecture, you need to have multiple computers, right? If you have a number of them, many of them with a larger number, then you probably need to store them in multiple racks, right? And each of the computer, each of the server will need to be assigned with role. One of the role that you have learned at last time is the name node, right? The name node is responsible for storing the metadata of the file. It will store the location where the blocks of files are located. Data node are the actual working horse, the workhorse of the model of the system that is kind of store part of blocks of data and perform replications. Now you will also see that the name node also have the secondary name node, right? So that's unnecessary to talk about it. Well, you may have the client on the edge node storing here in order to be able to access to the whole cluster. Now let's talk about important thing here. You see that there is the node. When we talk about node, we are actually talk about a server, right? A computer. You can install a process called job tracker to a server. Job tracker would perform something that is quite similar to name node, but instead of storing the location of the file, it would track the job that is submitted to the cluster, and it will coordinate the interaction between nodes and through the task tracker, which is a types of workhorse that work on the local node. Okay. Right. Actually, I forgot to do the sound check. Let's do it now. Do you hear me right? It's not like I'm talking alone without anyone here, right? So if you hear me, yes. Okay. All right. Okay. It should be better than recording at the university. Actually, I I I think because I don't know how the COVID, how long, when will it will when will it end, right? We are wondering about that. So maybe, yeah, I will move my gadgets, my equipments to the university, or maybe having another set over there, so that you can have like better quality communication here. Yeah, I'll do that soon. All right. Okay. Back to the topics. So we in the development of Hadoop, you can see that in the HDFS form the foundations of the system that it store data in distributed manner. Now, in terms of computation, Hadoop version 1.0 use MapReduce as the way that you can access the computation on the big data cluster. You need to write program in the MapReduce way. Back in 2014, when big data just come to Thailand, most of the company that use big data back then have to write programs in MapReduce. When I start working on big data, we will have to create a system using MapReduce as well. It has been thought that the big data would change the world really quickly, but it turns out that writing program in MapReduce is not that easy, particularly if you want the program to be more sophisticated. You want it to contain a lot of complex computations. So it is a type. It kind of limit the widespread of the use of Hadoop big data. But in the version 2, the MapReduce is changed to MapReduce version 2, which instead of directly access HDFS, it would have the layers of Yarn, the resource manager, and the resource manager would now taking care of the managing resource, the management of resource that allow MapReduce and other data processing to connect to that. We will take a look at the architecture, the old architecture of Yarn and how it works with MapReduce and also with Spark later on. All right. So how does it work, right? So this lecture would concerns with just that. How does MapReduce work? We have multiple nodes. We have data nodes, right? And each data nodes store data. We want to perform computation on that. There are two roles related in Hadoop version 1. Let's start learning about version 1 first. In Hadoop version 1, there are two roles related to coordinating the task. The first is the local role, right? That you can think of this role as the process that perform computation. We call that the TaskTracker. TaskTracker would kind of spawn the task that would be run on the data node. The task to be something that access and compute on the data node. And the job tracker would track the progress of the job on different data node. Right? So usually it would be assigned to another server entirely so that it would not be overloaded, just like the name node. If the job tracker want to access the data on any part of the system, it has to talk to the name node in order to know that these files are stored on which servers. Okay, so here are some basic summaries, which I think is nice. So I brought it up from this link. The job trackers would run on a separate node. Usually it would not be in the data node because it need to keep track of the multiple jobs at the same time. Think about job tracker as the manager. Right? You have manager, and then you have the members of the team, right? Manager need to manage, right? Manager cannot actually perform the task themselves because there are a lot of resource related issues that need to be managed so that the team will have a good performance. So that is the responsibility of the job tracker. So in terms of the program, the job tracker is just a daemon or a background process that kind of support the MapReduce execution. This job tracker and task tracker is replaced by resource manager and application managers in MapReduce version 2, which we are actually using in your VM. But you can you can still learn about them, and then you can compare the difference between the new version. And actually, I would say that when you learn about this architecture, try to compare them across different types of systems. This is not a new concept. In fact, you can see that the roles of job tracker and task tracker is just like working in teams in human world. It's just like name node and data node. It is like directory and BitTorrent peer-to-peer communications, right? So there are a lot of analogies on job and task tracker and the work in this way. So what are the roles of the job trackers? Job tracker will receive the request on the execution of MapReduce, and then it will contact the name nodes in order to extract the location of data. It would find the best node, the best task tracker nodes to execute the task. Usually this will be estimated in the proximity to the data so that it would be able to access data quickly. And the job tracker also monitors the task tracker, and it would process so it kind of process the execution of the task in Hadoop cluster. If job tracker is down, HDFS will still be functional because HDFS does not rely on the job tracker, it relies on the name node. But you cannot execute MapReduce, which means you will not be able to execute Hive and authors process that author service that relies on MapReduce. All right. So that is the role of job tracker. For the task tracker would run on data node. Mostly on data node because you want to run program on data nodes on all data. These are the roles that well in version 1 you need to assign to the server. This is replaced by node manager. Okay, the tasks like mapper, which we'll take a look later, what they are, what this is, mapper and reducer, these are executed in the data nodes, and it is controlled by the task tracker. Think about task tracker like the name said. It is the process that spawn the task on the MapReduce task. So it can spawn the map task, it can spawn the reduce task, right? Or the shuffling or the author task as well related to the MapReduce. The task tracker will need to communicate with job tracker for sure, right? You need to communicate with another to get things work. If task tracker fails, job tracker will still know what task it is to perform on that node. Job tracker can assign that task to another node to perform the task. So this is quite reliable if you think about this in terms of performing the task. It is just like working as a team. Right? You have the manager of the team, you have members of the teams, and they work together to get the task done. In MapReduce version 2, when we have yarn, okay, the architecture would be different. We have multiple nodes, the multiple workers, and each node would contain the node manager, and we have the master here, the resource manager. This is like the job tracker and the task tracker. But instead of thinking about job and task and for MapReduce, these resource and node managers also manage and administer the author, the resource to author services, to author tools as well. So client need to submit the job here, and then the resource manager will make the resource request. You can see from this line. So the resource manager will have to manage the worker. Node manager will report the node status to the resource manager, and the applications that is spawned here will make a request for the resource. Resource manager can assign the resource to the node manager. Okay, and MapReduce is executed locally. The container will have to talk to the application master, the application that is run, in order to say that the state of the execution. Then application would again request the resource to the resource manager. Things work similarly for when we learn about Spark. It works similar to this one as well. You have container called Spark container that is also run on different workers. These Spark containers will communicate with the application or Spark application on the local computer, on the the local workers. And all of them, when they need to have more resource, when they need to use resource, this application will contact the resource manager to get resource. So this work like operating systems. You can compare the way that Yarn work to a kernel in Linux to the resource manager in Windows. Okay, now let's take a look at how MapReduce work. And if we want to write program in a MapReduce way, what do we need to do? Just the name suggests that you need to write two functions. Or I would say two files, two code block. Right, two functions would do. You need to write the map program and the reduce program. Okay, the map program would map from the raw data to the intermediate version. Reduce would take the intermediate version and summarize them. Okay, sorry about that. And summarize them into the format or the thing that you want. You can perform MapReduce on top of MapReduce to get the task to be more sophisticated, to be more complex. So I will take this example of word codes to show you how it works. I'm not going to switch back and forth between the code and the program and we're writing a program to show you here, because what I will show you later on here, I'm going to explain about the process. And then you see the running, because there will be a particular command that you need to use in the current version of MapReduce in order to execute the MapReduce. Because why is that? Because right now it's not like because you need to access MapReduce through another means rather than executing MapReduce as the main processing. You need to access it to, for example, the one that is in my slide, accessing it to the Hadoop streaming interface. And it will allow you to do that. Okay, so let's take a look at this example. The objective is that you have a large file. You have a large document, let's say Wikipedia documents, and the size of Wikipedia corpus is about multiple gigabytes, if I remember correctly, for Thai language. If we talk about multiple languages, it will be quite large for that one. And you want to count the number of words. Why do you want to know that? Because if you know the total number of words, you can determine the distribution of the word. You can use that to allocate resources for storing let's say the representation of the word. Okay, so for example, if you learn further, there will be concept of embedding, there will be concept of word representation. You can learn about those representation and store them when you create an AI system. So let's say we have like that. We have a large corpus, a large size of word files, and good thing is that we have one word to a large size of word, one word per line. We want to count the number of times that each word appears in the file. We want to know how many times that it appears in the file, and then just that we want to count the number of words, which means that we will know the distribution of the word at the end. Why do we want to do that? For example, we might want to do that in order to do the web analyzer, to do the log analyzer. We might want to do that if we were to perform text mining. We want to know which word occur more than the other. We might want a pair of words rather than just one word, right? We might want to have a pair of words, which is called bigram, in order to create a model about the text. And we might want to know the distribution of those bigram. Running program on a computer, even though you have a fast computer, will be slow because this is data intensive. You have a huge size of data. Then you need to have a way that you can process the data, the whole file at the same time. And that's actually the idea of this. So let's say we have one word input coming in this way that you have a key and value pair. In this example, you have one word per line, so that each line would contain one word, right? You think about it as a key, right? You can group the key, and the value for each line would be one, right? In the input, so it would be, because you have just one word for each line. So the input in that case would be something like a simple one word per line like this one. The map step, the map program need to do this. It need to map from the input to the intermediate key value pairs. Right? It need to map to the intermediate key value pairs. Luckily for us, we don't have to do anything here because each line already contain each key. But imagine if we take Wikipedia data. Let me show you the Wikipedia data. Say Wikipedia. Okay. If you take a look at the Wikipedia data here, you can see that the text is stored in such a way that they are not separated one word per line, right? You need to separate them somehow because this is like the raw input data, right? They are not in the input format that I talk about. But somehow this text format will need to be processed, and then it need to be processed in such a way that it would be mapped to the key and value pairs, right? So it would be for each of the node here that have key and value pairs, it need to be mapped into a list of key and value pairs, right? The value here in different application, the value here may be different, may reflect different things. But the value in the intermediate value pair can be, it would represent the same thing, like it can be the number of words that exist, or actually it can be just one for this word, and then you can have reduced step, summarize them all. So basically, to talk about this, I would say that the map task is to just spread things. You want to spread things into key and values so that it will be easy to summarize, right? This is the map step. Then it comes the reduced program or the reduced step. By program, I mean you need to write, for example, two files. One file, Python file contains the map.py. Another would be the reduce.py to do the reduce. The reduce step would take in the intermediate key and value pairs and then perform grouping so that the same key would have a multiple instance of the value from the method, and then you can perform the summarization of these things. It doesn't have to be the number though. You can have different things here. It can be something like categorical values. It can be other things. So it depends on you, the way that you would perform map and reduce. Then in the reduce, it would summarize this whole thing to be just the final output. So one key, you would have one key and value, another as well, another key and value here. You can see that MapReduce kind of allow you to work in the distributed manner because you have to spread things around first. And then you can use multiple computers to summarize things up. And that make the process faster than calculating in just a normal computer. Okay, so here is the MapReduce. There is the kind of the phase before the reduced phase. You can see that this is the group phase. This process is it is the intermediate level of the MapReduce. So once you get the intermediate key value pairs, or between them, between obtaining the intermediate key value pair from the map and getting and reporting the intermediate key value pair to the reduce, you can add another process which is called shuffling. The shuffling process would perform just like the name suggested, to shuffle, right? It will shuffle the input or the output from the map, so that will be the input to the reduce. Okay, so the basic shuffling is to sort the key automatically, but you can still have different type of shuffling. Okay, so in summary, the MapReduce input is the set of key value pair here. Users need to supply to function to program the map, which will map to the list, and then the reduce, which will get the resulting here to get the final output. The K1V1 is the key value pairs, right? And output is K1V2 in the summarized step. You can again, let's say, concatenate this MapReduce with another MapReduce, and big data analytics back in version 1 works like that. You have like a sequence of MapReduce that form a workflow that you want to process. For example, if you want to create the let's say topic model, topic prediction using MapReduce back then, right? That writing it in the machine learning style is quite hard. So we need to, if you want to use MapReduce, let's say we can just take each word would have the scores, then you can map the word to the number of words that exist there, and in the reduce it would kind of aggregate the score of that word to the document, and then you would have each document on how many score, how much score that it has in terms of the whether it would be a sentiment analysis or whether it would be the topic score. Okay, so for word count using MapReduce, the pseudocode would work this way, and then do take a look at my code on how you can write a program to do that. The map function need to take in the key and values. The key can be the document names, and the value would be the text in the document. And then here it would need to emit the key that will be used to summarize in the reduce phase. So it would need to emit the word and say there's one happening, right? For the reduce, it need to take in another key, right? This another key would be the one that is emitted from the map, which is the word. And this will be the value that obtained from that. So from here, you can see that you can modify this algorithm in various ways. For example, you don't have to emit one here. You can emit the values that you look up from the table to get something like the sentiment analysis, right? You can emit, you can say that you detect the keywords here, and you can get something like keyword counting program. And yeah, and other thing, right? You can think about the emission from the map to be a different way. It can emit the numerical values, it can emit the categorical values, whatever you want. And in the reduce, it would take in the values. And for each of the count of V in the values, it would kind of aggregate them up and then emit the result for each word, right? This reduce would be applied to each group. So the execution of the program, we start with, we have the user program of the MapReduce. And then the data are splitted beforehand. This is a must. You cannot have the data on just one node or the data communicate online. It needs to be stored on the multiple computers first. And user program would, well, in reality, user program will connect to the TaskTracker or the what that's it called? The resource manager, and then spawn the task, right? For connect to the TaskTracker, the job tracker will connect to the TaskTracker to spawn the task, and then you have the task on the workers to work as the map, and those that will work as the reduce. The master or the TaskTracker would assign the map and the reduce roles to different server, different nodes. And then The data will be read on different workers, right locally, and then shuffling, sort, and use on the computer, on the workers that would perform reduce, and write the output. Okay, so this is the way that MapReduce work in the architectural manner. In the data flow that you saw there, the input and the final output would be stored on the HDFS, right? Because you can see that, well, it will be stored, it will need to be stored on the HDFS first, and at the end it will be written to the worker, to specific worker, meaning that once written, the worker will need to duplicate as well. Again, we need to report to the name node that there is this file existing. Name node will need to then assign that the blocks will need to move, not move, duplicate elsewhere on which computer they need to move to, right? So you can see the process that interrelated with the reading and writing of the HDFS files. So the task tracker, the job tracker, would also calculate and then try to perform map tasks that close to the physical storage of the input. Intermediate results will be stored on the file system locally, and then used in the reduce task. Okay, and reduce and output will be stored on the computer that perform reduce tasks. So how does each process coordinates? There you can see that there is this master process, or the master process that we need to assign the map and reduce to multiple computer. So you have the master, right? The master would track of the task status, right? So what is the master here? We are talking about the job tracker. We need to track the task status, the status of the task, multiple tasks, right? On different computers. The idle task will get scheduled to the workers. And when map is done, then when the map task is completed, it sends the location, and then the reduce would need to retrieve that data. The server that contain that will work on the reduce will need to retrieve the data, the chunk of data, if needed, from the mapped server, right? Right. Master would push that, right, by telling the reduce there's file there, they will retrieve that out. Master would need to get the worker status periodically to detect the failure. Once failure happens, right, if the failure is on the map, and that it is the worker failure, map task, if the map task is completed or in progress, this will be, at the worker, they will be reset to idle so that it can be rescheduled again. If the reduced work and the reduced worker will be notified that the task is rescheduled to another one. So think about this as, suppose that we have a member of the team that cannot do the task. Then the task that is assigned to that member of the team will need to be rescheduled to another one. And then the manager need to also inform a person that will perform the task, that will receive the results that there is certain rescheduling there. Yes. Thank you. Okay. Let me share it. I mean the battery. Thank you for telling me here. Switching camera and battery is smaller, so thank you. Actually, this will be problematic for me because when you see that there is the that the camera switch off, it means that there is a certain problem in the synchronization in the video, and then I will have to align them. Okay, let's move on quicker because actually today's RTA will have to present his work at the conference at 3 p.m. right? So he can demonstrate to you guys first here, and then he will have to hop into another online room to make presentation for his master level work. Right. So let's move on here. And so this is just like in the team working. Okay. If the failure occur at the reducer, occur at the reduced worker, then the in progress task will be reset to idle. And if the failure occur at the master, then the MapReduce is aborted, right? If the manager is down here, you cannot report the results because manager keep everything here. That might be the weakness of these systems in terms of redundancy. But in any case, this is the way that the failure is covered for the system. So how many of the reduce and the map jobs do we require? There's a rule of thumb here. Let's say we have M map tasks and R reduce tasks. The rule of thumb is that you usually need M and R with a larger numbers than the nodes in the clusters, because in the computers in the nodes, you can have parallelism in the computer as well. For example, my computer here contains 4 hard drives, right? So it means that you can read from the 4 hard drive at the same time. They are different physical systems. So that means if I were to use this in the MapReduce manner, you can actually parallelism at least 4 tasks on different disks. So usually M and R will be larger than the number of nodes. One chunk per map, so it needs to be large. But these are actually managed automatically later on by the resource manager. And usually R is smaller than M because in the reducer, you can see that the map has to do things with the raw data, and it's harder. But reducer take in the prepared format, and then it can reduce from the result. And that is actually easier. There's also another process that you can put in for I would say before doing the reducer. That is, you can have this process which is called combiner. Combiner try to combine the results that you get from the map so that the reducer would perform less tasks there. So usually the map task to produce many pairs in form of like KV1, KV2, it can be the same K. So instead of performing, putting everything to the reducer, which you can have a tremendous multiple lines of data there, you can kind of combine them first, and then you can fetch the results of the combination to the reducers. So think about it as the pre-reduce. You need kind of combine the map results first. So the combiner would pre-aggregate the results for the reducers. Okay. Usually the combiner can be something that is similar to the reducers, just to combine the results from multiple computers together. Because let's say we perform the word count, and we have hundreds of nodes, right, or tens of nodes. There can be multiple chunks of data stored in these 10 nodes. And when you perform the word count of the same word, you can aggregate the data first so that the data that form in multiple lines that you emit can be combined earlier and then you can aggregate it by sum later on in the reducers. This would work is if the reduce function that you want to use is commutative and associative. Right? In mathematics term, these two means that you can switch place. Right? You can perform one before another. But if not, then you don't really need them. Right? You can put everything into the map function. So here is the MapReduce with and without combiner. So on the left-hand side is the MapReduce without combiner. We start with the input, and the input is run, and you get the mapper results 1, mapper results 2. And then after emit here, shuffling and sort, and you get the key and the results here. Reducer would combine the result together. Then you get the reduced output. This is without combiner. With the combiner, from the input, you get the mapper first, and you can see that there are multiple A, which can be combined before shuffling. Right? So kind of combine them together, and then the shuffling, and then the result. Right. All right. So this is the combiner part. With combiner, you have an option to specify partitioner and a lot of names, right? In this, think about them as different roles to perform distributed computing tasks. Right? MapReduce is easy. Just map them into like throw everything. Like you want to sort things up, you would just spread everything out to see them, then you sort them, right? That's usually the way that you take care of your clothes in your closet, take care of the work on your table, spread things out, and then you can organize them. That's the MapReduce. Then combiner is like you kind of combine them first, and well, you can specify the partitioning. Partitioner decide which key and data to go on which server. So how does it work? Input from the map task created by having the split of multiple files, right? You get the multiple chunk of data and then do the mapping, have the result. And for the combiner, it would combine the result like these two together. So you get this one. For the reducer, we need to ensure that the record with the same intermediate key, like A here, would end up at the same worker, otherwise it would not be summarized. So the default partitioning function is to hash them and hash the key and put them into that. But you can specify it manually. Let's say if you don't want to use the key hashing, you can do something else by specifying the partitioning function. Partitioning function would kind of direct how these would be reduced on which server. So those are the way that MapReduce work. We have a map that spread the data into the intermediate key value pairs. We have reduce, which will summarize the results together. We have combiner, which can combine the map results first, and then we have partitioner, or the partition function that would control the assignment of the data on the results to the node index. So that's about it in MapReduce. MapReduce work together with Hive. Hive is a way that a program that you can interact with, and then you can make a query with Hive, and then it will spawn the MapReduce task to extract the data. So in the Hive, you can query in the simple manner like this one. And then it will spawn the MapReduce job to do that for you. So how does Hive work? You will learn about this later on after the midterm. So I will just go over them really quickly. From the user interface that you use Hive, you will make a query, find where the data is stored, and then it would go to the execution engine to spawn the job in the Hadoop so that it would extract the data out. Once you obtain the data, it will return and fetch to the UI. So that's how it works. MapReduce works as the workhorse for Hive, and you will learn Hive next time. All right. That next is the demonstration. I will leave this part to wide, and because we got about half an hour left for today's. All right. Are you ready? Why?
Yes.
All right. So I'm going to allow the share, and I'm going to stop the share. Now it's your turn.
Okay, thank you. Okay, for my part now is to demonstrate you how to run the MapReduce program on the VM. So if you follow the slide, you will notice this code mapper and reducer.py here. This is just like in the slide. We read the for the mapper code. We read the input in each line, and then we strip. Strip means you get rid of the heading and trailing white space, and then you split the line into the word. Using split means you split the sentence using the space. Then for each word, you in the form of word and then the character 1 here. So the output from this mapper will, I will run this on my VM.
The output would be the image, because by printing, it means that you are printing it out to the standard output.
So for example, I have my mapper file here. So if I read, so the output from the mapper would look like this. Echo, and something here. Okay. And then I use type, and then I run the mapper.py. Yeah, so the output would look like this. It just and then for the next step of the MapReduce reduce step. The reduce step is just you sort this intermediate output by key and then perform the reduce. So for the reduce is just you counting the same word until you find that you are at the end of that the same word, and then you emit the output that you count, and then you start counting the word again. So let me show you here. So first I need to sort.
You can write. I will talk about during your typing. From the code, when you review, you see that the code is actually very simple. You just go through each word and then count them. Right.
Okay, so here is I sort the intermediate output from the mapper and then use reducer to reduce it down to like summarization of the word occurring in the file. So from my input, I have testing the test file. You will notice that the test is occurring twice, and then the other occurring only once. So you can see here file 1, test 2, and testing 1. So this is a simple MapReduce program on how to do the word count. For more complicated program, you can just you can modify your mapper or reducer to let them emit whatever token you want, and then reduce it. So this is just running on the local machine. So if you want to run this on the cluster, on the Hadoop cluster, you have to have 3 things. First is the Hadoop streaming library, which is located in your Hadoop installation folder. Second is you need to have your input file on the HDFS. And third is the mapper and the user file. So let me show you how to like transfer the file from my machine to the VM first. So you can use the FTP client like FileZilla or WinSCP. For ease of use, you can just use a Jupyter to upload the file to the VM as well. So Jupyter, I will use Jupyter Lab here. And then I visit this IP address at port 888. So let me copy this. Place it here and port this port. You can open your Windows Explorer and then you can drag and drop the file into here. So this is the easy way on how to like transfer the file between your computer and the VM. So I have my mapper file, reducer file, and my input already. For the last thing that I need to have is the Hadoop streaming library, which is located in the Hadoop installation directory. So I shut down the Jupyter Lab. To obtain this library, you have to navigate to your local Hadoop share and then Hadoop tool and lib. You see it's located pretty deep in the Hadoop installation folder. And if you list the files in this folder, you see that you have this Hadoop streaming 3.1.3.jar here. You can copy this jar file to the home folder for easier referencing when you dealing with MapReduce tasks. So I'm gonna copy this CP and then the jar file.
Jar file is the Java binary. Usually it will store Java program or Java libraries.
And then I will move it to my home folder. Not move, copy. Sorry. So if I change my directory to my home folder, okay, I have my my streaming library jar file here. Then I have to put this file, my input file, to the HDFS. So I can use simple HDFS command, Hadoop, and then put this file, Sherlock, the text to the HDFS. If we list the file, Hadoop, okay, my input file is here. So now we are ready to run the MapReduce program.
Right now the file is in the cluster.
Oh, other thing is your Python file need to have the execution permission. So to add the execution permission to this file, you can use the Linux permission command like chmod, and then a mean all plus x mean add the execution permission to all the Python file in my current directory.
What Y is talking about here, because usually if you take a look at the screen now, it is RW, but there is no X. X means execute. Right now, the permission for the file is only to read and write. Right? To get the execution, you need to do chmod, right, to do the execution. All right.
Okay, you run this command. It will alter the permission of the Python file. If you list the file again, you will see that we have the execution permission here, the X here. So now we are ready. So the command in running the MapReduce is Hadoop jar, and then the streaming library, which is Hadoop streaming jar, and then we have 4 parameters that we need to set, which is input. Oh no, mapper first. Mapper. We have to specify the mapper file for our program. My mapper file is located at the home folder and mapper. Next argument is the reducer. So my reducer file is located in the same directory as mapper. And for the third argument is the input file, which from in this case is located in the current directory of my current user, which is the username test user. So the input, which located in /user/test user, and then my input file is sherlock.txt. Okay, I will open my new terminal to show you where my input file is.
มันเป็น Hadoop อ่ะนะ
Yes.
Yes, it's Hadoop. So this is my input file, which located in root, user, test user, and sherlock.txt. So I will use this file here as the input, and the output. I want the output to be stored in my home folder in the HDFS as well. So /user/test user, and then let's name it Sherlock out. Okay, so this is the command on how to run the MapReduce program on the HDFS. So you can just press enter here. Oh.
You need to do the
reduce. It's reducer. Sorry. It's reducer. Okay.
These are the logs of the execution. The above, you can see that the job submit split to 2, and then it will report the status of the MapReduce, starting with mapping. Now the mapping is done 100%, and here are the summary of the results.
So everything's done here.
Mm-hmm.
Okay, so if we navigate to our home folder in the HDFS, so you see that Sherlock out is here as a directory. So let's see what's inside this directory. So in this directory, we have 2 files. Success means the out job is run successfully. And the path 0000 here is the output from the mapper and reducer. So if we read this path file, so I will just use head to read it. And then path here. So this is the output of the word count program.
Okay. So from this, you can see that the simple codes that you can run on your computer locally and will work as well in the Hadoop cluster. And that means you can test your program using your local execution, using your local computer to test the map and reduce. And then you can deploy that onto the Hadoop cluster later on. All right. Thank you. Bye.
Okay.
Which part? Which part that you have the problems with? Is it the mapping? Is it the reducing? That's all right. That's all right. Or is it Is it the code, or is it the code, the commands? If it's the command, just can just recap it later on, right? Because actually in the command, you just need to specify, it's on my slide as well. You just need to specify the mapper, the reducers, and the program. Yeah, let me recap it. So here, there's Hadoop, and telling that you run the jar, which means you are going to run the Java program. And this is the Java program you want to run. And this is the mapper file, the reducer file, and the input file to the mapper. And the output folder that the file's output should be stored at. Okay. And let me switch back. Why? Thank you. Let me switch back to the slide here. Here in the slide, you can also see the code of the mapper and reducer. For the mapper, what the mapper would take from the input from the standard in. Standard in means the results that it got from the standard input. In this case is the file that we use. And then you can write the program that perform computation on each line of the standard input. Yeah, and for the reducers would just count the number of words. You may wonder why not using pandas or numpy to aggregate. The reason is that what I'm trying to do here is to just show you that you can work on MapReduce without really need to have the libraries. Using libraries is also fine. Well, that's nothing heard about that, but you need to have libraries stored in the node before then. This is on the assumption that there's no library needed. Right? So if you use library, code here would be reduced a lot. Be like strip using NumPy and others. Okay, and you can see MapReduce work by here when you sort the output. You can see that the intermediate key value pairs look like this. Then when perform reducer, it will reduce the output like this. And this is on your local computer. But once copy the file and then run on the actual, note that the file here is different though. In Wise version, he copied it to the local path and then used the full name. For me, in my case, I use this one, which is on Hadoop Home. So it's different. So it depends on computer to computer. The one you use is, you need to use, in the VM, you need to perform just like that. What I say. And these are parameters that you can put in. There's the combiners, you can specify that, reducer, mappers, which you can specify to this. Right, and the rest are the same. Okay, why I forgot that you need to also share the lab.
Okay. Okay, for the lab, your task is similar to the word count. So we are not working with the text, like raw text. We are working with structured text, which is the log file. So the dataset this lab is the Hadoop log analysis, which is from my cluster at the A Square lab, which is the 38 megabyte of HDFS and YARN log. So let me explain on the structure of the log first. So the structure of the log that we are going to use is log4j formatted log, which log per line, which comprises of four tokens. First is timestamp. Second is log level. Fourth Third is the source of the log or the category of the log, and the fourth is the message. So we're gonna dealing with this type of log only. If you see other types of log like the Java exception or the command message, you can just discard it. So let me show you the file first. So here's the file that you're going to use in this lab. So you can see that you for the log4j format log, you have one log per line here, like this, all the way down to the bottom. You will encounter another types of log like this, the command message. You can just discard it if you read it by each line and then you found that you cannot pass it as the log4j format. You can just discard. So this is the file that
on how to discard them. That's up to you, right?
Yeah.
Think of the way that you would reject those lines by yourself.
Okay, so this is a file. So for your task is to code from the lecture, modify them to answer this question. But first, how many logs are there in each log level? So in log4j, we have 3 levels of log, which is info, warn, and error. How many logs are there in each level? So this is the first question. On the second, how many logs are there in each type of source? The third, what is the average length, which in the case of the aspect of the number of characters of the message in each type of source? And fourth, which day has the highest number of log occur and how many? And for the last question, which source had the highest number of error level log occur? So you have these 5 tasks. Modify the mapper and the reducer to answer this. So for each question, what to take is the modified mapper or reducer file code, and then the result. So should we extend the deadline here because
yes,
next week,
because next week will be the exam.
Okay.
So the deadline will be the week after that.
So it's October 9.
Yeah.
Okay.
October 9.
Or October 8.
Let's see. Yeah, it's about that. I will put the deadline about that time.
Okay.
Right. All right. Right. So the deadline will be after the midterm. And
9 better.
yeah. And next week you got your midterms. On class marker, I will post the link about the middle of next week. Yeah, it can be 9, 10, about that weekend, right? So that's it for MapReduce. Do you have questions about MapReduce? Or it can be about the exam as well. You have questions you want to ask. I talked about that earlier in this lecture. There will be 40 multiple response, multiple choice questions. You have 2 hours to work on that. You need to access I'll post the instruction later on. That will make things easier to understand. The exam will start from 1:30, and then you need to access the exam before 2. Okay, you have 2 hours to do that. And the results will be sent to you immediately after the test ends, which means about 4 or 5 p.m. All right. And the topics that will be included in the exams are everything up to this point. Okay. I would urge you to ask if you have questions to the Facebook group so that everyone will see, and we will respond as soon as we can, especially if you do not understand on which part of the content. In the exam, you need to so in the exam you need to access class markers. So be sure you can access the internet during the exam time. Okay, and well, we are on the trust systems here. I trust you guys to do the right things. Cheating is unacceptable, no matter whether you are on any levels. So yeah, I trust you to not doing that. Well, this is the COVID era. So I will try to make the exam harder to compensate for that. Okay. You can, well, I configure the test to be, you can reconnect to the test if you got disconnected. Given that you access to the exams during those half an hour, okay? You need to access to the exam during those half an hours. If you access to the exam and then you reconnect to the internet, it will still use the same cookie, the same session, the same IP to connect you to that. You have to use your ID to access the exam just like last time. Don't use your friend ID, because once you use your friend ID, the system will log that as the attempt. And yeah, it will be problematic there for sure. And I will know who do that because I will get your IP. All right. Don't complicate things. Otherwise, I will need to find a way to complicate your life further. I don't want complications. Okay. Well, ask me. I would suggest you to talk to me before the day before the exams. All right. So I will, after the class, I will upload the video to the groups as soon as I can. Okay. Should be within today. All right. So if nothing else, that's it. Have a good day, everyone. Good luck, wife, on your presentations.
Okay,
Yeah.
thank you.
All right. So bye-bye, everyone. Have a good day.